Cool.
And if people have their face cams on and you don't want to be part of it, I mean, you could try. Does it get the face cams, Daniel?
It depends on the view. So
Okay.
because we're in screen sharing, it should only be recording the screen share.
All right, cool. All right, then that's fine. Okay, cool.
And yeah.
Bear with us, guys. This is our first time doing a Zoom meeting as well. Like for this big amount of people. We're going through what every I guess professor has gone through for their first classes, and they usually been a mess. So trying our best.
Also, Armando, I just emailed you the questions if you want to show them.
You emailed it to me?
Yeah.
Okay. Okay, so we're also going to be filling this out and posting it on our website. Here, I'll show it to you guys. But it's going to be just general questions. It's kind of like just the frequently asked questions to most of the senior designs. And we're going to create like a folder on our website so that later on, if people can make the meeting or they don't know exactly what one senior design talked about, we're going to have that on there. There's like an archive for today's meeting. So we'll also be you're recording it now, Daniel?
Yes.
Okay, cool. Okay, so I think that's all the announcements I had. Nick, if you're ready, I think I need to stop sharing my screen so you can share yours.
Yeah.
Okay.
All right, cool. Whenever you're ready, Nick.
Can you guys hear me?
Yep.
All right. So, hi, I'm Nick Barbieri. I'm the Vice President for the Intelligent Ground Vehicle at CSUN. I'll be presenting today with the Cognition Team Lead, David Kaya. So just some of the stuff we'll be talking about today is how the teams are broken up and guided. We'll talk about the competition for the Intelligent Ground Vehicle, some of the systems on the vehicle, and our budget and fundraising options. So just a bit about the team. The faculty advisor is Dr. Nanikola. We have a president and vice president, and then we have 5 chairs or leads. I'm here with the cognition team lead, David. He'll be talking a little bit later. Basically right now, this project has been dead for about 3 or 4 years because the professor that originally ran it left CSUN. So we're basically taking an old project right now, reviving it, and figuring out how all the systems work in order to make a new one in the next upcoming semesters. Our IGV lab right now is in JR 1123. We aren't, just like all the other senior designs, we're not working in there right now, we're working from home. So research is our primary focus right now. One of the good things is the hours are pretty flexible once school gets started back up. If you can't make it to the scheduled times, you can go whenever you want. And as long as you're putting in work, it's not that big of a deal. We will be meeting during summer and winter break if the school is open. If not, then we'll just continue our research. So I'll let David take over from here to talk about the competition and the system.
Hi, everybody. I'm David. I'm the cognition team lead. And basically our goal with the IGV is to create an intelligent ground vehicle, which means we're creating an autonomous vehicle to compete in the IGV competition in Michigan. So it happens every June. 40 plus schools compete, including teams around all across the United States and even internationally. There's actually quite a big showing from India. And the competition consists of the following. There's the design challenge, the AutoNav challenge, and the IOP challenge. So first looking at the design challenge. Next slide, please. Next slide, please. Yeah, awesome. So looking at the design challenge, there's 3 different parts to it. So there's the written report, which includes like just a written outline of all our innovations going on with this thing, specs, and then there's the oral presentation in which we have to be able to directly present the work that we've done and show intimate knowledge of our design to the judges. Lastly is inspection or examination of the vehicle to allow the judges to see clearly what the robot can do. So here's our rules and requirements. So we must fit these dimensions of a minimum of 3 feet of length to a maximum of 7 feet. Our width must be between 2 to 5 feet, and we have to fit under 6 feet. And other considerations that are important are we have to meet a minimum speed of about 1 mile per hour, and we can't go over 10 miles per hour. The power must be supplied on board, and we must be able to carry a payload of a cinder block, which is about 20 pounds. So other considerations that are important and that provide quite a challenge are just considering weather conditions. Because it is in Michigan, we have to design for rain, high humidities, and high temperature. This is important because we're dealing a lot with sensitive sensors. So all of these factors are really, really critical when designing the robot, just to make sure we don't fry any of our stuff. Other design considerations that prove quite a challenge are designing this thing to go over grass. The field is almost completely grass. So we have to really design our robot with proper suspension to really reduce noise for our sensors so we could get accurate readings on this stuff. We also have to travel over uneven surfaces, mud puddles, speed bumps. There's ramps as obstacles on the field, which are about 20 to 15 degrees. And we even have to design our robot to go over a sand pit. Next is our emergency stop. This is a really important aspect to our robot. This kind of just allows the judges to safely operate the robot. Ones that we are working with now are physical e-stop, which is a mushroom switch. And it's just basically a physical break in the circuit. And the other one that we have to deal with is a wireless e-stop, which has to work up to 150 feet away and has to be waterproof. So this is the AutoNav challenge, which is the most important, or the main goal of the robot. So it's got to navigate an obstacle course, search for navigational waypoints, stay inside the boundaries of the course, and appropriately avoid flags and barrels. So all of this has to be done autonomously. And we do this by creating a cognition, if you will, in which like the robot can accurately map its surroundings and navigate through its virtual path. This is like the cool part of the robot because it's very cutting edge technology. All the advances that's happened in this field have been within the past 15 years. So it's really awesome to just, I don't know, hop on the leading edge of that. So we're kind of seeing the fruition of that in warehouses in which they're designing these kind of robots to just kind of do that. But this stuff is really quite new. So here's an example of what our robot has to do. All these little dots are kind of barrels. And what our robot does is it navigates through these white lines. It has to sense these white lines, navigate around the barrels, and hit all the stars, and then cross through a fence, hit all the stars on the other side, and then return back to its position by crossing through a flag field, which it has to detect these little flags and then color code them correctly, which I can pass on or can only pass on one certain side of them. So if you want to show them the animation. Yeah, so So what's it called? How do we do this? How do we avoid the obstacles? So we have to program the robot to build a map by one, being able to isolate white lines to detect these lanes. And then two, we have to distinguish obstacles like flags and barrels. So we do this by using vision cameras, laser rangefinders, and LiDAR sensors. So one interesting aspect of this is image processing, in which we use certain techniques to isolate features that can be translated and mapped. So we do this by using like saturation limits of pixels to detect lines and colors that we can use to appropriately recognize obstacles such as flags. You can see here three different techniques that we use or can be used. There's the blue technique, in which is really good for recognizing colors. There's a hue technique, which is good for recognizing lines, and then saturation, which is good for both, but is computationally expensive. So part of our what we do is just decide which one works best for our robot design. Next is the IOP challenge. This stands for interoperability profile. So basically, we have to show to the judges that a robot can intercommunicate with itself, that it operates coherently with precise goals and is cognitive of its surroundings. So this would include like being able to introduce itself to the judges, being able to recognize that, be able to tell the judges, you know, what it's doing, be able to hand over momentary control to the judges to manage its system conditions. The other three ones would be, next slide, please. Being able to tell the judge its velocity state at any given time, be able to report its location and where it's going, and then be able to transverse to 4 specific waypoints or areas of interest autonomously. So here's an example of all the stuff that we are able to work with. So we've got several different sensors here, such as cameras, GPSs. We've got our DC motors, LiPo batteries, laser rangefinders, LiDAR sensors, e-stops, and IMUs, inertial measurement systems, and then a PVC or PCB board. The cool thing about this, I know you guys are all mechanical engineers, and a lot of this is kind of outside of our field per se, but I think like the best part about this project is it really rounds yourself out, especially for those wanting to get into robotics, because you're working so much with a lot of these sensors, which are really prevalent in robotics industry applications today. I mean, you won't be able to get a job anywhere without running into at least laser rangefinders and inertial measurement systems. So just being able to get your hands dirty and round yourself out, I know I've been able to add to my resume quite a bit, because through this project, I've had to learn LabVIEW in a more intimate way, and I had to learn Python coding. So if you guys really want to join or get into robotics and learn about how these sensors work and how, you know, these robots are programmed, this is like a great entry into that. Dr. Nandakola, she's got she is so good at offering opportunities for students to get inside the robotics industry. It's really great in that respect. And I'm going to hand it back to Nick. Oh, Nick, you there?
Oh, sorry, my mic was muted. So you guys are probably wondering how much these all cost. It's about $60,000 for a new vehicle with all sensors and whatnot. So we do need to do some fundraising and whatnot. Our fundraising chair right now is Rithik Das. He's a Associated Student Senator, so he has a lot of options and stuff to help us get money. So one of our current sponsors right now is the International Student Engineering Association. they're going to be helping us with some money, but over the next couple of semesters, we're going to have to be doing some fundraising and whatnot. So we'll need help on that end as well. As for now, that's basically the presentation. So if you guys do have any questions or anything, you could ask us, or if you want to wait until after the rest of the senior design presentations, you could just send us an email or whatnot. But yeah, this project's really good if you guys want to, like David said, get well versed in robotics. A lot of the technology we're using are the stuff they kind of have on Teslas and whatnot. And we're also looking into getting more people from like electrical engineering and computer engineering to kind of teach the mechanicals some of the skills that they're lacking in. So if you guys do feel weak in one area, if you want to kind of get the experience you need in, like, say, electrical engineering or computer engineering, you definitely will have some resources if you join IGB. But yeah, if you guys have any questions, we're more than happy to answer. Thank you.
What are some roles that MEs would have in this project?
So we need, well, I mean, most of our team right now is ME. We only have a couple electrical, so we need people for designing the suspension of the robot, the frame, a lot of the mounts for the cameras and whatnot. We also need people to work with LabVIEW, like David said, Python coding, trying to improve the code. There's a lot of aspects from mechanicals. I mean, we have a mechanical team that just solely focuses on the mechanical side of the robot. And yeah, if you guys, it's a ME senior design. So, I mean, you guys want to join it. You don't have to be on mechanical, but you can be. So there's a lot of options.
Yeah, to be completely honest, my entire team, including myself, we're all mechanicals, and we all had no prior knowledge to really cognition for robots in general. So this has been just one big learning process for us to try and catch up. So honestly, don't feel scared to join in subjects that you're not strong in, because like I said, it's just a good way to round yourself out. And I was able to go and interview with Haas recently just because they saw that I knew how to program certain things, and all of that I learned basically just a semester.
Thanks. I have one more question. What exactly is a LabVIEW? I haven't heard of it yet.
Yeah, so LabVIEW is a visual code, basically. Once you take ME 335, you'll learn it. But yeah, it's a visual code, and it's really easy to learn because of how visual it is. And so have you taken ME 209 yet?
Yeah, and 309.
Sweet. Yeah. So basically this code works by passing variables along wires instead. And operations are all controlled, instead of by function, they're controlled by visual interfaces. So this program basically works really, really well with virtual interfaces meaning it's really easy to create controls for this program and user interfaces for this thing. So it's an intuitive language, and it's not that hard to pick up. So
Cool. Thanks.
Any other questions?
I have a question.
Okay, go ahead.
Who would we contact if we're interested in this design project, or is there an application process?
You could either contact me, the president, or Dr. Nandicola. I can go back. Her email is right here. If you just want to send an email to there, if you guys want to volunteer.
Okay. All right. Thank you.
Yep, no problem.
How involved is Professor Nandicola in the project?
She's in the lab every single day. So, I mean, we have people working there. Well, we had people working there when school is in session every day, basically. And she'll be in there, if not 5 to 6 hours a day. So if anyone has a question, or she's there to help, give guidance, whatnot. So yeah, she's there a lot.
Okay.
Yeah.
Okay.
She's also not like, how do you put it, like super controlling like some other professors might be. So that's one of the nice things, is she gives enough leeway to figure stuff out, and she definitely prefers what the team leads and president wants to do in the direction of the IGV.
Okay, awesome.
Can I ask a question?
Yeah, go ahead.
So I don't know if you guys discussed this, but like, there was an IGV team like previously. Are you guys gonna get all that information, like all
Yeah, we have
Okay.
all the teams from 2014 to 2003. We have all the reports and everything. So
Okay.
we're basically just trying to teach ourselves the 12 years of knowledge that they built up. So
Okay, that's cool. So it's a continuing thing, basically. You guys
Yeah.
aren't starting from nothing.
no,
Okay.
we're continuing,
That's
and then
really
we're
good.
gonna start a new project probably next year, I think.
Cool. Thank you.
Yep.
Okay.
So I think if that's it, we can go on to the next
Yeah.
senior
That's
design.
it.
Yeah. Thank you guys
Nick.
for your time.
Thank you, David.
Thank you.
Okay, so next is Thea with smart prosthetics. Are you here, Thea?
Yeah, I'm here.
All right, awesome. Are you ready? Oh,
Am
yeah.
I
there you
sharing?
go.
Is it sharing?
Yeah.
Okay, cool.
Thea was
All
actually on
right.
last year's ASME board, so shout out Thea.
Okay. Okay. Good evening, everyone. I'm Thea Bihimino, a team member of the 2019 through 2020 cohort for Dr. Bichet's Smart Prosthetics Senior Design Project. So this Smart Prosthetics is a research-based design senior project which allows students the freedom to develop a design completely on their own. And so the issue with upper limb prosthetics is that there isn't a lot of development in comparison to lower limb prosthetics. This results in unaffordable, commercially available prosthetics for upper limbs. Therefore, research and development performed in universities is viable information that would result in affordable and reliable upper limb prosthetics in the future. Can you guys hear me okay, or am I like talking too fast?
It's good.
Okay.
Good.
All right, so as mentioned, the Senior Design Project allows students the freedom to develop a design that is new each year. Each cohort implemented something new every year. The two previous cohorts used shape memory alloy wires, also known as SMA wires, for actuation. And the first cohort focused on a design that mimics the human hand aesthetic, and the second cohort introduced a clever lever locking system, which you can see on the slide. So this year's mission statement for our cohort was to design and develop two low-cost and electrically powered transradial prosthesis arms with novel sensing capabilities and increased gripping and lifting strength. So with that, our cohort decided to design two arms this year and to completely eliminate the use of SMA wires. Our two designs are the My Own and Hall & Oates arms. Our cohort introduced the application of haptic feedback to provide an amputee a sense of feeling, a Wiffle tree subsystem that allows for the entire arm to be actuated by one motor, and also pattern recognition. So this is the internal components for the My Own arm. And this is the internal components for the Hall & Oates arm. And this slide just shows the grips that our arm was able to perform for this year. And so this is also our budget breakdown. Compared to the other senior design, our budget isn't that high, but we're actually able to accomplish a lot. And as you can see, we have a lot remaining in our budget. So I think for the next cohort, if you do use a lot of the budget, you're able to accomplish a lot more than what we have. And I think we also accomplished a lot with not spending that much money already. So Anyways, if you want any more information or you're interested, Dr. Boucher is actually holding an info session tomorrow at 11:30 a.m. and here's the Zoom link. Thank you.
Any questions for Thea before we move on? All right. If you guys have questions, she has we'll put the link also on our Slack channel for tomorrow's info session for that. So next is Morphing Wing with Tommy.
Yeah, you here?
Tommy,
All right.
right.
How you guys doing?
Pretty good, sir.
Oh, good to hear.
You ready to share? There you go.
Yeah.
Is it just you, Tommy, or Adam as well?
Just me.
For sure.
All right. So I just want to introduce myself. My name's Tommy McLennan. I'm one of the project leads for Smart Morphing Wing. And I'm doing this presentation today on behalf of our faculty advisor, Dr. Peter Boucher. I'd just like to introduce you to the Smart Morphing Wing ASME info session. So before we actually go into our project, we have to kind of talk about what technology exists today. And a plane has a wing and tail with control surfaces that help control the plane in flight. And you can have flaps, elevators, and rudders on these control surfaces. And they're great, but they're non-continuous, which means that they have gaps in the surface, and you'll have vortex formation, and it's drag inducing, so it's pretty inefficient. So what Morphing Wing wants to do, what morphing technology wants to do, is to have a very seamless airfoil there. That way you have better aerodynamics and you don't have those inefficiencies. So we have a couple different technologies. You got span, chord length, sweep, twist, and camber. And what span does, it actually expands the length of the wing. The chord length will increase the width of the wing. Sweep will change the angle of the wing. Twist can be either a variable twist or just a section of the wing that twists. And then camber morphing is a little bit more difficult, but if you draw a line on the cross section of an airfoil that goes from the leading edge of the airfoil to the trailing edge, you take that line, fix it at the leading edge, and have the trailing edge morph up and down. You now have a very complex control surface that morphs the entire tail. Morphing designs have been around for a couple of years, and it started kind of at a component level. Dr. Boucher, this is our 4th year for the morphing wing. And so in the 2nd year, they actually used a corrugated airfoil, and they used the same SMA wires that Thea talked about for the prosthetics to actually actuate that. And that was great, but you couldn't actually fully test it in the environment that it would be in, which is flight. So there's another team that actually did this transformer down in the bottom left. And that's actually just span morphing, just in the wing, just to demonstrate that single technology. Now, last year's team decided that we wanted to eliminate all of the control surfaces that are traditional. So what they actually did is span morphing in the front for the wings, and then camber morphing for the tail. That brings us to our design for this year, which is Metamorph 2. And along the same lines as what the team wanted to do last year, we want to eliminate all those control surfaces and use only morphing technologies. So we ended up going with a twist morphing wing and a camber morphing tail for the back. Now, that gives you an idea kind of what morphing wing is, but what the actual project is and what we do over the 2 semesters is really based on an 11-page research paper that we submit to the AIAA. And then we actually do a presentation at their student conference. We weren't able to do that presentation this year due to the coronavirus, but we did submit that paper. And that paper is actually going to be researched, and that's backed by our design process, all our computational and physical testing. And that's really all that's required for the research paper. But our team wants to get first place. In the last 2 or 3 years that we've actually done this competition, we've always been second place to USC. So we feel that designing our own fully functional UAV and doing a test flight will put us in first place. So what we do is the fall semester, we do research, our PDR, CDR, and testing. And then as it goes into the winter break and then into spring semester, we do the manufacturing, some more testing, our paper, and then our competition for AAA. We also do C Symposium and Senior Design Project Showcase, where we do very well in those competitions. Now, I kind of wanted to go through just the basic level of what we did this year as far as starting from scratch and getting to our full UAV. And what we did is we looked at conventional UAVs that exist right now in the military. We looked at other experimental UAVs and could try to get an idea of the size of what we're capable of building here at CSUN. And so once we got all these design parameters, we realized that the whole process is a very intense iterative process of designing. You put inputs into how the wing's going to be, that changes how the tail's going to be, that changes the design of the fuselage. And once you realize something doesn't work, you have to go back and change something. So we developed this MATLAB code that helps us take into account the weight of our wings, and then it gives us our outputs here for our net lift versus wingspan and chord length. So we can find the sweet spot of what the size of the wing needs to be in order to lift our UAV. And then we take that information and we actually put this into another MATLAB code that gives us the size of the tail based on the inputs for the wing. So as we're doing that iterative process with the wing, we're actually inputting it into this program and getting results for the tail. And both teams for that are now talking about what works and what doesn't work. So these tools are very useful in communicating that. Now the tail team also, they designed this, this camber airfoil plotter. And so what it does is we're able to change these A and B inputs and then change our dimensions from the previous app of the tail. And we're able to actually output what's needed to create the plot of a cambered airfoil. And we're able to use that in our analysis later on. We do take that into our analysis with CFD, the computational fluid dynamics, which is something that we've never touched before. It's very similar to doing FEA analysis with SolidWorks that you do in 386, but it has a mind of its own. I personally didn't work on any CFD stuff, but I know the guys that did work on it were pulling their hair out. But it was a very useful tool that's allowed us to virtually study our morphing technology before actually doing any prototyping, any actual testing physically. And it gave us favorable results. One other thing we did is a comparison of our morphing technology, the camber morphing in the tail, versus other technology that exists on conventional planes. And we actually were able to plot this based on the angle of attack of the control surfaces. And you have our coefficient of lift versus coefficient of drag, which is kind of a ratio of efficiency of the airfoil. So you can see that here, and in the blue line for our morphing technology, it proves to be a much more efficient and much stronger control surface than existing technologies. That gave us the confidence to go in and then start manufacturing. So as you can see here, we started manufacturing in picture A, that's our fuselage being attached with the horizontal stabilizer. In picture B, we have the fuselage getting set up with the structure, the carbon fiber structure that we're allowed to then put the skin on. In picture C, that's going to be our molding process from the Keck lab with our carbon fiber hollow wings. And that's under vacuum bag. I believe that was in the paint booth in the machine shop. Then you have a lot of 3D printed parts for our tail section. And then finally, in the last images on the bottom, you got the actual completed tail and then the twisting wing that we need to design. So we did actually get the morphing technology working on this XM2. Unfortunately, we weren't able to do test flight. Our pilot came in, told us that we had a couple things to fix, and then as we all know, the campus was closed. So it's very unfortunate because I think if we were able to do that and put that into our paper, as well as be able to present that we have the first fully functional UAV, we definitely would have gotten first place. So it's a big letdown to get like 95% there in the project and not be able to present what we completed. But with that being said, it was a great project. Definitely encourage anybody that's interested in it. Like Thea pointed out, there's the link for Dr. Boucher's info session on both of his projects tomorrow. I also put a link up here and Dr. Boucher's email. That's his, you can look over the past projects that he's worked on. And then there's actually a submission file at the top on how to apply for both of his teams and get a little bit more information on that. With that being said, if you guys have any questions.
Yeah, Tommy, I have a question. So your MATLAB programs that you ended up implementing within each sub-team, was that based off of your suggestion, or was that already within kind of this whole senior design project? That's just engineering approach.
I don't have a picture of the equations that are used, but there's really just a handful of equations that are used to start doing that process. And so when we started doing that kind of by hand, we realized that it was going to be, once the first run through of all those equations happened, we realized we're nowhere in the ballpark of a working UAV, and we're going to have to do all that over again. We realized we need a better approach to it. Of course, Dr. Boucher is the faculty advisor for MATLAB for the 309 course, so he definitely is interested in that aspect and helped us along the way. I didn't have a very good professor for 309, so it was good to have Dr. Boucher there to help us along, especially those that didn't know how to use it. But it's not really a requirement. He allows you to use any tool that you need to use, but he's more than happy to show you something that you don't know, which is really MATLAB and using ANSYS was two things a lot of us never really had experience with. So it's pretty cool to get that experience while we're working on the project.
Right, and that's great. So you don't have to keep taking steps backward and then move forward and whatnot. So I think that's really cool. And one other question I had was about just did you think that the project was more based on like designing and manufacturing and research as opposed to like flight performance, airworthiness, control systems and whatnot? Because it's more based off of your, I guess, morphing tech and your concepts, right?
Right. It was a little bit of both. I'd say that a lot of us pushed to make this more of a manufacturing project. Obviously, the research is there for the paper, and that's the main deliverable. But there was a lot of us that wanted to see something physical. So I think we pushed for a lot of that. But there's a lot of people on the team that are looking to go back and get to CSUN and get their master's program, or go to another school and get their master's program. So they wanted to do more of the research. It was good to have that we had enough people that were interested in both to really fuel the project. You could even do both. I mean, there are a lot of people that did a lot of manufacturing, but also went and did that ANSYS analysis. I'd say it's a mix of both. It depends on what you really want to do.
Right. The controls part seemed interesting with the SMA and just the whole schematic that you showed. That was pretty interesting to me. So I was wondering if it was more based off of that, or just design and research and conceptuals.
A lot more. We were supposed to use, I think, about 20 sources at minimum of technical papers that talk about morphing. So in a lot of those, there's the component level stuff, like in the picture with the SMA wires. And we take that information. We don't really reinvent a lot of stuff, but we take technology that's already out there at a component level, maybe improve on it for our design, and then put it onto the plane to now make that the fully functional plane. That's the main intention. So there were a couple things we like optimized, say for the camber morphing, we optimized it for weight. But it's a design that's been used on many other morphing wing projects. So we're not really reinventing the technology there, just trying to be the first to have that fully functional UAV.
I see. Awesome. Thank you, sir.
No problem. Anybody else?
Okay, so thank you,
Yeah.
Tommy.
Oh wait, Armando, I have a question.
Yeah, go ahead.
Or actually two. One, about how many people are normally on the team? Do you know?
Dr. Boucher doesn't like any more than 20. We had 18 on the team this year. I think they had maybe 15 on the team last year. That way, I think it's not a huge project to work on, but it gives people the ability to kind of move around a little bit, but not be too overwhelmed by the amount of work that the entire team has to do.
Awesome. The other question, well, I guess two-part question. One, how does fundraising happen for your team? And then, are you involved with like other companies? Do they donate any materials for your project?
Yeah, we had a problem with the transition for our Morphing Wing Club with the AS last year. So I think we wasted a lot of time this year trying to get set up with that. So we didn't get to focus on additional fundraising that we'd want to do. We did get a donation from the company that I work for in aerospace. And then we also reached out to a company that does a flexible carbon fiber fabric, and they do it. I guess they're the supplier, and then they manufacture purses and bags and luggage and whatnot out of this fabric. And we had a sample of that from a couple of years ago, and we reached out to them, and they donated prototype for fabric that they already have. So they actually donated probably, I think it was 5 or 6 3-yard sections to us. That's what we use to actuate a lot of the morphing technology. So that was pretty good donation, but I think next year's team has the opportunity now, because we're set up for the club. They don't have to worry about that. Get the money from the club, and then on top of, we have a budget of about $3,500, and it might increase for next year. But now you also have the opportunity to go out and fundraise and maybe get a couple $1,000 more to really boost up the project. Because I think ours was, we used our whole budget, but there's definitely a lot more that we wanted to do, especially with carbon fiber, that just wasn't within our budget. So the next year's team has that opportunity to maybe do that.
Awesome. Thank you.
No worries.
Tommy, I had one more question about the whole funding issue as well. Who's the right point of contact, would you say, in your work environment to go and speak to about Morphing Wing and about funding for the project?
I typically would say either like a director of engineering or the general manager, and that usually will involve them bringing in their finance team, or bringing in somebody from HR. But it's hard to say. I mean, right now we're in a situation where we can't even go out. But even before that, I think a lot of companies don't encourage you to show up on site and ask. I definitely recommend reaching out maybe to the HR department and see if you could do something with those. Like I said, the director of engineering. I know all the director of engineers that I've met in my career so far have been like super nerds about these projects, and they're really happy to kind of help out in any way that they can.
Right.
Even just showing up to presentations. But how you get that contact is sometimes difficult. So I've seen people actually show up at my work just to ask for a in-person interview on the spot, and it's been successful for some people. So you might want to try that if you're not getting anywhere with the email.
So if not with email, just kind of, I guess, go and kind of network and see if you can kind of get in touch with people who would be able to help out, I guess.
Yeah, it's just the ability to be able to show that you're passionate about project. Obviously, there's a fine line to not cross there, but they have access to receptionists and lobbies and whatnot, where you're able to at least show that you're trying, and I think that speaks volumes for a lot of those in the industry.
Great, thank you.
No worries.
Okay. Thank you, Tommy. Our vehicle, Remy, or is it William Remy?
Most people just call me Remy, but whatever.
Okay.
Doesn't matter. As long as I know you're talking to me, I'll answer.
All right, you ready to go, Remy? Do you have your PowerPoint ready? Or
Yeah, I got a PowerPoint here, and I can share the screen. Yeah.
yeah.
Okay, cool. So let me start that then, and I guess we'll just get into it. There's that. Put it on the reader view so it doesn't look so janky here. Reading view. Okay, so that's showing up good for everybody. Everybody can see that.
Yep.
Okay, cool. So, like you said, Armando, this is the human-powered vehicle team, of which I am a member. I'm also a team lead for the components team, sub-team, and I'm also the technical advisor and change board. So that's what I'll get into those roles in a second here. Let's see. So this is our mission statement. It doesn't necessarily matter what it is, it changes every year for every team. But generally what the project is about is just creating a sustainable vehicle that's human powered, basically, which is exactly what it is. It's effectively a bicycle. That's kind of our deal. But the thing that we focus mostly on is, we try to do everything that we can to do everything ourselves, to limit our purchasing except for necessary parts. Like nobody's going to make a crank for a bike. We go buy those, but insofar as we can, we try to manufacture everything. And we've done pretty well over the years in terms of winning competitions. We do have a competition, which I'll get into a little bit later. But this year obviously is a little bit different. We do have a competition that we're actually doing. It's the same eFest, but it's basically just based on a presentation video that we sent in, instead of any kind of actual physical competition, the situation being what it is. But at any rate, so here's our team structure. Obviously, as most people probably know, Cacciatorians is our project advisor. Our chief project engineers, Annabelle, she kind of oversees basically all of the sub teams, and she's kind of the point of contact for everything that happens between the team and any donors or any companies that we have contact with. She's basically our point of contact for all of that. And then I'm the project technical advisor and change board controller, meaning that's mostly a second phase situation in terms of manufacturing, because as we're all aware, things never really go as planned. And when they inevitably don't, I basically am the person who decides how we move forward and what we do to fix the situation in order to minimize impact on all the different sub-teams that are involved in whatever particular thing is bringing up an issue. And then as far as our sub-teams go, we have systems integration and testing, led by Alex. And they are basically our systems engineers. They are responsible for, in the first phase of the project during design, they oversee any interference checks, the top-down model. They organized all of our fundraising efforts, did all of that. And then the second phase, that's where the testing part comes in. They basically come up with all the testing plans, and they do all the execution for our ASME required testing, and even the testing that's not technically required, but we run anyway. And then we have our frame team, which Rupen is the lead for. And they pretty much do what it says on the tin. They're responsible for the frame of the bike, for all the design, analysis, and manufacturing. And we have components, which I'm the lead for. And we're responsible for pretty much everything that moves on the bicycle. So it's everything that makes it stop, go, and turn, which is a lot of moving parts. And we're responsible for a lot of the design, well, all of the design of all of those things, and the purchasing of any necessary parts that we wouldn't otherwise fabricate. And then we have the fairing team, which is led by Maddie. and they're responsible for the fairing, which is you know, a aerodynamic device to help you go fast, basically, and reduce drag. We only really use it for the drag race, but it's incredibly important, and its benefits can't be understated. That's a lot of composite work, and they get into a lot of the CFD during the design and analysis. Not so much any kind of like stress testing, really, but they're dealing more with fluids and with composite work. Then we have the innovation team, which is led by Adam, and that team is it's an interesting team because they don't really have any constraints or necessary guidelines. They just kind of this year, for example, this year they designed and implemented an anti-lock brake system using Arduino controllers and small battery packs and Hall effect sensors. It's actually a really, really cool setup and rather, you know, innovative, for lack of a better phrase. Previous years, there was a two-wheeled bike that they made this like this hydraulic actuating kickstand that when the bike would stop, it would pop down, had little wheels on it. There was one that was it was like a self-steering mechanism, and using Arduino also in that situation, they basically had this little hydraulic actuator that would steer the bike for you and keep it on a path. Really, really cool stuff. So that seems really interesting, and they bring a lot of interesting skills to the table there. But that's our team structure. As far as the project flow, there's really not that much theory involved necessarily. I mean, I suppose you could say there is, but it's more of an application of all the theory that you would learn in like a machine design class. And for some particular sub teams, it would be, you know, a fluids class or composites class that would teach you the things that you need, like if you're in fairing or innovation. Innovation also takes a lot from the 435 classes and the 335. I would say it's about split, outside of about 10% theory, it's about split evenly between design analysis and manufacturing after that. We use pretty much all of the labs and stuff on campus, including the big supercomputer that runs some of the really heavy-duty CFD analysis. Obviously, we use the Haas lab. We have a room in there and a little space on the floor. We use the machine shop, Keck lab. We make use of Marco's room in the Keck lab over there for all of our welding and a bunch of the like fabrication that we do that has to do with the frame. So that's pretty much that as far as team structure and kind of how the project runs. I would say if I had to say a way that Cash runs things is he's fairly hands-off, which personally I really appreciate because it gives us the room to kind of make our own decisions and run the project the way that we see fit. And only when we are either completely blowing it or we have no idea what to do will he step in on his own and say, hey, this is maybe not going so great. Why don't you try this, whatever. But he doesn't ever force your hand on things. And I actually really appreciate that. So this is our vehicle this year. Well, it would be if it had been completed. We didn't actually get to finish the fairing, but we had a three-wheel tadpole semi-recumbent rear-wheel drive. Semi-recumbent means it's not completely laid all the way back. Obviously, rear-wheel drive. The frame was 4130 chromoly. Fairing was carbon fiber with Atlantisoric reinforcement. And like I had already mentioned, anti-lock braking was the innovation for this year. So our competition would have been in, Michigan this year. We obviously didn't go, but this was the first year that was the case. Generally speaking, the furthest people have had to travel in the past would be to Las Vegas, or I think actually they went up to Reading one year or something like that, so somewhere up north. Maybe it was Sacramento, I'm not sure. But generally we don't really travel that far, but since they kind of disbanded the eFest West, and I don't know if they're actually going to bring it back, it's likely that any future competitions are going to be either in Michigan or in Georgia. And the competition is 3 days. It's a Friday, Saturday, Sunday. It's usually 2 days travel time, 1 day there, 1 day back, unless you are part of the team that's transporting the vehicle, in which case it takes about 5 days to get there and 5 days to get back. So if you're into driving super long distances with nothing to look at, that's the job for you. So this is kind of where we stopped with our construction and manufacturing. I mean, there's no pictures here of somebody running it, but I've got some videos later. We did construct a trailer, which is that little thing that you see up there on the top left. That's because this year was the first year they actually had a trailer event, which is, it's a weighted trailer event. So you pull up, you get out, you go throw some weights on it, then you can do a lap with the weights on it. This is during the endurance race, which was one of the events of the competition, alongside the men's and women's drag and a design event. But the endurance race is obviously, it's based on how many laps you complete in a allotted time. And when you do the weighted trailer with a lap, you get extra laps. So we built that in order to train our riders team for that. You know, you can see everything there. I mean, it looks almost exactly like the model that I showed you just a minute ago, which is great. It's always nice when things come together. Obviously, it wasn't without its hitches along the way, but it worked out pretty well. In terms of volunteering, I think it's not necessary, but I would highly recommend it if you can do it. Like me personally, I didn't volunteer at all. Oh, there you go. There's Ryan. Look at him go. Ryan's on the components team, and there he is doing our slalom. There, it's that's one of the events in the endurance race, one of the obstacles rather. Okay, so there you go, fun little videos. It's not required. I didn't do it because I didn't have time, but it always helps, and especially starting a new project with a bunch of people, it helps if you kind of have some idea of what you're getting yourself into. The way you get the application is you would want to talk to Cacciatorian, send him an email, or after this, when we do some questions and answers, maybe I can just get some emails from people, or however we want to do this. I don't know. Yeah, they do a fall spring, and then only a few people will be doing a spring fall. Like we have right now, we have 5 students that are 486A. And they're going to continue on and finish in the fall. The only downside to that, obviously, is that you don't really get to see any one thing all the way through. You kind of help people finish the tail end of one bike, and then you start anew, but you don't get to really go all the way with it, which is unfortunate for somebody in that situation, but it is what it is. I would say the application process is a lot like a job or an internship. You really do have to apply, and you gotta submit a resume. It's kind of a whole big thing. Catch takes it pretty seriously, and there's only 24 spots total. So if it's something you're interested in, definitely try to jump on it, because they do fill up fast, and it's worth going after it either way. But that's kind of the deal. These are just some pictures of previous bikes that have finished. This was last year's here, the Black Turtle. This was Deadliest Catch. This was Catch 22. This was Catch 22. I don't remember which one this one was, but Deadliest Catch and this one both were first place prizes. This was second place, and this was second place prize. Here's just a photo of competition. In terms of extra skills, none are mandatory to bring to the table if you want to try to join the team. Nothing is, you don't have to know what you're doing with welding or coding or composites or mechatronics or machine shop or whatever it is. You don't need to have any of that, but it does help. It does help a lot. You not getting on the team, but just you on the team operating. It does help. It makes things a lot easier if you already know what you're doing and you don't have to learn it on the spot. Because you will do it. You will weld, and you will use the machine shop. And if you're on fairing, you will work with composites. And if you're in innovation, you will probably work with some form of mechatronics. It's going to happen. Fundraising is done all by the team. We do get some money from the department. It's very little. We mostly fundraise. And we do that through events set up by SINT. We do that through donors of either companies that people go out and solicit donations from, or a lot of times teams' family members will donate. Companies generally donate material, not so much money. Like 3M donates a lot of foam. kind of to a lot of the projects, but we kind of get that set up. There's a shop up the street from CSUN. It's called Domestique. They do a lot of discounts for us and give us a lot of information. And if you need like 3-dimensional models for things, they do have that as well. As far as attendance is concerned, oh wait, not yet, not there yet. As far as attendance is concerned, summer is required for sure. That's when a bulk of the pre-design happens, and your PDR will be probably right before, the week before school starts. So a lot of work gets done in the summer, but it is sparse in terms of attendance. There's just a lot of work going on. Winter is absolutely required. That's when all the manufacturing happens. We try to get a jump on it as much as we can. In terms of time commitment, it's probably, I don't even know. I mean, it's 5.5 hours on paper on the like school calendar, but it is much more than that. I mean, how much more kind of depends on what's going on with the project. I mean, if everything's on fire and everybody needs to help, then it's probably going to be a lot. If everything's fine, it's probably not that much extra. I don't know, it's hard to quantify. I do want to mention before I finish here, which I'll be finished in 1 second, is that there is a orientation that we're doing not this next week, but a week from Monday, or the week starting April 19th, we're doing an orientation for people interested outside of this. If you know anybody that's listening, if you know anybody that's interested, we're doing an orientation that week. There's going to be more information forthcoming, much like the way Aero and Morphing Wing and Smart Prosthetic are doing it this week. We're going to be doing it in about a week and a half. So that's it. That's my spiel. That's Human Powered Vehicle. Are there any questions? Here, let me stop sharing my screen here. There we go.
There's a question in the chat about Cacciatorians being the advisor next year.
Oh yeah, there we go. Yeah, of course he will. He's the only one that does that.
As far as summer, how do the hours look like in terms of like, do you have to show up to schools from like the morning, or you can go in whenever you can?
Summer is generally, in terms of like hours, that's what I was trying to say, is summer is a little bit more lax in terms of attendance. There's just a lot of work happening, right? We, over summer, I think we met maybe once a week, or once every other week. I was usually about once a week, and it was usually after like 6, when people are at work or people have internships or whatever, and if you can't make it, you can't make it. It's just that there's a lot going on in terms of research and preparation for the next phase, the actual design phase that comes after that, that takes up the entire fall semester.
Any more questions for Remy? Okay, so we'll be moving on to Searle, and representing Searle will be Seth. Seth, are you here?
Yes, I'm here.
All right. You ready to go with your?
Yeah. Yeah.
Awesome. Thank you.
Give me 1 second. Let's see. All right. Y'all see it all right?
Yep.
Okay. My name's Seth Klotzel. I'm the project manager for Searle at CSUN, which is the Systems Engineering Research Laboratory. We are, opposed to other projects, we're much more of a research-based project. We don't really have a competition or things like that we really aim to go to. There is one kind of conference that we're looking forward to going to in the future. It's called GIFIX, which is the Joint Field Interagency. Shoot, I forgot the X. It's like a basically where a bunch of people can bring their projects to put them on display. It's put on by the Air Force, which we are funded by, and we're also funded by NASA. But so what we've kind of named our research is the simulated and live unmanned test environment. So basically, what we're doing is we're creating this this infrastructure that is composed of basically two different subsystems. One is our mobile ground control station, and the other is going to be these drones. Our CSUN mechanical robot and design is kind of a part of the drone operations, but it's a very special type. That's one drone that we are completely designing and making ourselves, whereas other drones are going to be kind of off-the-shelf drones that we are then putting sensors and other devices on that we can use. So our overall kind of arcing goal in our research is to create this system that helps these other supporting systems in natural disasters. So we would have our mobile ground control station, which is a van that would show up on site and work with these other departments to help one, locate people. We also are putting sensors on our CSUN to look at like gases, like harmful gases and obstacles around, so that way we can help coordinate with mainly like fire department and paramedics on how to safely navigate the area. So here's the GIFIX. There was one coming up in May that we were hoping to go to, but now that's not possible. But so it's basically just to demonstrate our abilities to use these devices with other people, and in this environment, to help. Yeah, I mean, the main idea is to save more lives through natural disasters. So this is our mobile ground control station. Many of you might have seen this van in the parking lot outside Jacaranda. So this is the van that we're using for our mobile ground control station. There's going to be a desk in the back for 3 people, an L-shaped wall. This is kind of what the goals were for our design team. And so this is kind of just gives a layout of what the van is aimed towards. We had a mock-up desk made of wood in there, but that has come down. The plan is to use some extruded aluminum. I don't know if any of you have been in the Haas lab, but it is what the Formula E team is using to build their jig table, something similar to that. So we have a little bit of modularity with how our layout looks. There's just a few CAD models of our van. So there'll be 3 people in there, and then there's also a kind of standing room behind the desk for like commanders of the other supporting agencies that would be involved in these operations. So this is what our kind of the aim of the van. We just got the rooftop AC unit installed just before spring break, which was nice. That was a big thing that we were looking forward to getting done. We got it delivered before winter break, and it took some coordinating with the machine shop, and we cut the hole and everything for that. Solar panels will be installed in the future. Like I said before, it's more of a research project. So a lot of this stuff could end up being redesigned in the future. So that's kind of one of the benefits, is that a lot of this stuff is kind of open to whatever that team wants to kind of do with it. We don't have a 200-page manual about what our system has to look like and all these different parameters that we have to adhere to. So it's really kind of open-ended as far as how you guys want to take it and what you guys want to do with the research. So the CSUN is the drone that we are making. It stands for Compact Exploratory Autonomous Search and Rescue Rover. It was designed after one of the rovers that JPL is making called the Puffer. So this is the outline of what our design team was going off of for the Caesar. So basically, to create a small functional rover that can use this SARWI software, which was actually developed at CSUN by a computer software team, and it's an AI software that can recognize humans and interact with them. So that is what we will be implementing into all these drones, into this all of this hardware, to be able to communicate together and then back to the operators. So this is the design of the Caesar. It's being slightly changed right now. Some small iterations. We ordered parts and they came in slightly different size than what they were advertised as. So there's some small changes going on with that. It's currently has been printed from PLA, except for the wheels. They're a different flexible material, but everything was printed at CSUN in Dr. Lee's research lab. He's got some 3D printers, so that's what we've been doing with that. This is a camera, so that's it has LiDAR in it, and then a couple other cameras, and it has its own processing unit, so that's made that camera stick out. But then we have spots for other sensors, speakers, stuff like that, so that way this drone can detect like harmful gases, and then also be able to with victims that may be stuck to help analyze their situation. This is just a little bit of an exploded view of that. And this is, we have a couple of electrical engineering students that are also looking at designing our own like PCB. So that way we can minimize a lot of the space that these individual components take up. These are all just kind of off the shelf things that we're kind of using for plug and play. So one of the drawbacks to that is the amount of space they take up, rather than making our own circuit board that has all of these integrated in them. We can save a lot of space and weight, which then transfers to battery life and operability of the drone. This is just another view of it. We're using the NVIDIA Jetson Nano, is what's kind of the brain behind this, behind the Caesar. So if you have any sort of programming experience, I know HPV was talking about some of that. Mechatronics and stuff is really good. Right now, we're focused on a lot of the control and perception of the Caesar, which kind of comes with mechatronics, and then also 484, which goes over controls of systems. That's where we're at with the Caesar. We also, this semester, we started a new team called Drone Ops, and they're basically taking a bunch of the other drones we have in the lab and making them operable, kind of getting them running. There's a lot of stuff that we've kind of accumulated, and we're kind of piecing it together, getting it to work with different sensors, with GPS, with running off of a signal from a computer rather than RF through like a kind of like a remote control, different things like that. So this is a little bit more on the experimental side, but there is research going into with having access. The end goal is to have them connected through like a Wi-Fi mesh network, so that all of our drones are in communication with the mobile ground control station. And that's probably one of the biggest challenges for this team, is to make sure that all of the drones will be able to communicate with each other and not lose connection. This is the mesh network that we're currently using. It has 3 nodes, but this is what is currently being set up to run all of our drones and our network. These are some of the drones we have. This is it's called the Firefly. It's a vertical takeoff and landing UAV, which is beneficial. We don't need a runway or anything. We have it's called a Kraken, is that octocopter. That's another unit that we are working with. We have a few different types of quadcopters, and on the bottom is a Husky. It's made for like surveying, but it has quite a payload capacity and can perform many different tasks and be outfitted with a lot of different sensors, and other devices for perception and stuff like that. So that's is useful for what we're doing as well. If you have, let's see, real quick back on, let's see. As far as drone ops go, if anybody, or if you want to learn anything about ROS, which is Robot Operating System, that's what most of our devices run on. It uses Linux as the operating system, but that's what we're using. It's a little tricky to get used to, but it's not too bad to get the hang of. So yeah, with that, if you guys have any questions, any concerns, you can also, Professor Hartman is the one that oversees our project. It was previously advised by Dr. Ho, but he is now busy with this new ARCS project that he's on. So it has been passed off to Professor Hartman. However, Dr. Ho still is in contact with our project and what we do. So you can either send him or myself an email if you're interested. Just get more information. We can put you kind of on a list just so that we know you're interested. But do you guys have any questions?
All right, I think.
I have a question.
Okay.
Yeah.
Hi, Seth. It's Fern. So how is the learning curve for like your team members, since this seems like a pretty much a very big mechatronics project, and most people aren't taking mechatronics and or control systems until they're in their senior year or whatever. Like, how much would you consider the learning curve to be, or is everybody doing programming or
No, yeah, okay, good. Yeah. So not everyone's doing programming. Most of the programming is on our Caesar team because they are developing the entire Caesar from scratch. So that's where most of the programming is. Our mobile ground control station has virtually no programming at all. It's a little bit more hardware based as far as just, the desks and I mean the computers and a little bit electrical as well. And then our drone ops team is more of the kind of collaboration of all the drones. So it's not as much programming as it's more of kind of like a systems approach.
Mm-hmm. Gotcha. Okay. Thank you.
Okay, awesome. Thank you, Seth, for your time.
You're welcome.
So last but not least, it will be Formula, presenting both their IC and EV, so internal combustion and electric vehicle. And presenting will be, there's a lot of them here. Morgan, Jake, Sean, Fernando. I don't know who's presenting.
Morgan and I will be presenting, mostly
Okay.
Morgan though, but I have the slideshow here.
Right, awesome. Thank you.
Hi guys. Well, we do Formula SAE, and we build race cars. My name is Morgan. I'm the electric vehicle project manager for this year, and presenting with me today is Jake Forsmer. He's the internal combustion project manager.
Hi, Jake Forsmer here.
Yeah, so our team philosophy is to design and manufacture a Formula SAE compliant race car aimed to maximize total points scored at competition while remaining within the resources available at CSUN. Basically, Formula SAE is an international design competition. There are 9 or 10 competitions held around the world annually. We compete in what is now Formula SAE California. Unfortunately, due to the coronavirus, it got canceled. But that's the one that we'll be doing next year because it's only an hour and a half away instead of in Lincoln, Nebraska, and no one wants to go to Lincoln, Nebraska. Basically, Formula SAE is, you're posing as a fictitious manufacturing and design company, and your goal is to build a race car that follows a strict set of rules set out by SAE, the Society of Automotive Engineers. So in that time, you design, manufacture, test, and race a small open wheel race car. All the design work is done in the fall. You manufacture over winter and early spring, and then you test from late spring until your competition in June. Next slide, please, Jake. So the competition is points based. So basically, the team with the most points at the end of the competition wins. Static events make up about a third of it, and the dynamic events make about the other 2/3 of the competition points. There's a business pitch that's worth 75 points, and that's where you present yourself as the company going to investors, and you're trying to pitch to them why they should invest more money in your product so that you can make more. There's a cost analysis portion of the competition, and that basically is how much does your car cost? Basically, the lowest costing car gets the most points. And then there's the engineering design, and that's based on the theoretical design of your vehicle. So engineers from industry will come to design to judge the design of your vehicle, and you have to present all of your calculations and simulations and testing and validating your design with real world data. And then we move on to the dynamic portions of the event, which are, in my opinion, the most exciting. So you have the acceleration event, which is essentially a 0 to 60. The car with the fastest acceleration wins. There's a skid pad, which is a figure-8 to test the lateral acceleration capabilities of your vehicle under steady state conditions. There's an autocross event, which is what the entire competition and your entire design is based around. And you're building this weekend autocross race car that someone can buy. So you are trying to build the best parking lot destroyer. And then there's an efficiency event where you do, and that's wrapped up in the endurance event. So the endurance event is 20 laps. You have 2 drivers. They switch out halfway. It's on an average a 22-kilometer event, and included in that is your efficiency score. So for combustion, they measure how much fuel you use. For electric, they measure your initial starting and ending power with a power meter. Next slide, Jake. So we have our team goals that we set out every year. So we have, our improving our static performance, because we didn't do very well last year in the static events, primarily in the design event. So it's important to understand the validation of your designs and having presentation practice, improving reliability. We did not finish endurance last year. There was a small component that caused a much larger failure. So our goal this year was to improve the reliability for both vehicles. And then, our Formula SA program in terms of our club, including more volunteers and, maintaining equipment and, equalizing workloads so that people weren't, overloaded in one regard and, bored in the other. So that's more on the managerial side. Again, unfortunately, we didn't get to go to our competition like everyone else, I think, except for maybe Aero. But yeah, we'll get to that in a minute. Jake, next slide, please. So this is our design matrix. This is what Dr. Prince gave us to use for dictating the design of both vehicles. We heavily emphasize reliability as the largest weight, because at all costs we wanted to make a car that would finish all of the events. We wanted to make it as simple as we could, because again, if you understand a simple design, then you'll do much better in the static events, and you'll design something that again will ultimately be more reliable. Our third weight was performance. We still need a car that performs really well. And our last design criteria was cost. We still need something that we can that can do well in the cost event. Next slide, please, Jake. Actually, Jake, this is you. You should talk about your team structure here really quick.
Yeah, no problem. So I'm Jake. I'm the project manager for the internal combustion car for the 2020 year. We have different sub teams in the encompassing for that car, and here you can see the structure. We have the aerodynamics team, which is, and I'll get into all these subsystems in a little bit more detail later, but here you have the aerodynamics, which that's like our skunk works. They do all the magic stuff. You got chassis, and that's, Fern. He's over there. He's here. He's our chassis boy. And controls is run by Josh Shepard. They do all of the systems that the actual driver integrates with, or that the driver interacts with. So it's one of our weaker points, and it's one of the easiest actually to get right. But it does take some innovative thinking. So you have your steering wheel, and in all your systems, like your shifting system and your pedals. Like the pedals is one thing that's really overlooked because it has to be ergonomic and adjustable for the actual driver to be pleasurable to drive, but also be able to perform its purpose. And it's actually a lot more complicated than people think, and it usually is something that ends up getting redesigned and thrown together at the last minute. This year was Josh Shepard did a really good job at designing the brake, or the pedal box assembly. Another thing that gets overlooked often is the seat. It doesn't seem like it's that big of a deal, but it needs to be lightweight and needs to support the entire weight of the driver. And it needs to be comfortable. So the last few years, it's been able to support the driver, and it's been lightweight, but it hasn't been very comfortable. So you sit in it, and it's pretty, it's not unpleasant, but it definitely could use some improvement, and that's something we've done pretty well. And drivetrain is another one of our sub teams. They do most of our machining too, or all of our machining. So running all those Haas CNC machines that we have in the lab, where we have our VF4, our ST20, our TM1, those are all run by the drivetrain team. That incorporates like the differential and the sprockets and the half shafts and the wheel hubs, all that stuff. Then we have engine. That's probably the most popular team. They do all of the air intake system, and the dynoing is all done by the engine team. We actually got our engine dyno up and running this year, so that's something that we've been really excited about. I'm sure you've heard us dynoing in the Haas lab the last few weeks before we got shut down. And then suspension, that's another great team. It's very complicated, big emphasis on your understanding of statics and system dynamics. But it's a very rewarding team. As difficult as very rewarding, and it's really it's probably one of the most interesting in terms of like actual competition. The hearing the conversations over suspension design and all that. It's a cool team. So this is the 2020 IC car that we designed, and we got pretty far into manufacturing. Generally, the overall vehicle design is a single seat open wheeled race car. Our projected weight is going to be 326 pounds wet. We are by far the lightest car in the competition. Last year, the year before, we've always been the lightest car for quite a few years. That 326 pounds, that's without the driver. We're 61-inch wheelbase. The aerodynamics package is carbon fiber rear and front wings with electro servo actuated airfoils. So we have a drag reduction system, so those airfoils actually drop down in order to reduce drag during acceleration events. We have let's see what else we have. Our under tray is designed to be multi-piece, so it pins together or bonds together. I'm not sure exactly what we ended up going with. So that was an innovation for us. The redesign that we did. The frame is a 4130 DOM steel space frame. Our suspension is a four-wheel independent suspension with non-parallel unequal length A-arms, push rod with push rod coilover dampers. We have our drivetrain. We're running a Honda CRF 450 dirt bike engine, single cylinder 4-stroke. And then we're controlling that with our Megasquirt ECU. And then the intake plenum, which is that big, it looks like a gourd on the back of the car. That's our intake plenum, and it's really a marvel of design. I've had a lot of fun manufacturing it. I 3D printed that on our 3D printer with Nylon X, which is just carbon fiber reinforced nylon, which that was fun learning how to do. And then our muffler also had a redesign this year in order to better pass sound without stuffing it full of stuff. And then we have a Drexler adjustable differential and a pneumatic shifting system. And so, yeah, and then our wheels are also made out of carbon fiber. There's a lot of carbon composites work on this car, which is really exciting to do. Yeah, and I think that's about all I have to do. I think I'll throw it back to Morgan. He could talk about the electric car.
All right. So last year, just a brief backstory. Last year we tried to convert an older combustion car into an electric car. It was a great idea in theory because we would, get a rolling chassis, and all we had to do was install an electric drivetrain. Except that was an absolute nightmare. So we scrapped all that and decided to build our own car from the ground up. So as far as the Aero team goes, they kept it very simple, and they were just going to do a simple body and a flat under tray portion of the vehicle, no wings. That would just, increase complexity for our vehicle. We were, again, just trying to get a simple car going for our first official electric car. The chassis team had to completely redesign the electric chassis to house all of the new tractive system, the electric drivetrain. We had the addition of a data acquisition system. So because we've never built an electric car before, we wanted to closely monitor, all of the performance metrics of the vehicle to make sure we didn't have any big scary battery fires. We had a data acquisition team design an entire system from scratch. They did all of the coding themselves. They were all a bunch of computer science majors, and they made their own website that they hosted on a server. So the live feed would actually upload to the server, and you could view it on the website in real time. Controls, again, to keep everything as similar as possible to the the combustion car. A lot of the controls interfacing was simplified and basically doubled, so that we could just make 2 of everything. And again, like Jake said before, controls is very important because if the driver does not feel comfortable when driving the car, they're not going to perform as well. So all these things that are involved in the control system, the steering wheel, the pedal box, the seat, and the shifting system for the combustion car are all very important. And then there's also a proposal of passing more mechatronics related activities like the DRS system onto controls as well. So in order to maintain, our competitiveness, we're going to be pushing more mechatronics in the future for both vehicles, and controls will be handling that. As far as drivetrain goes, again, it's very similar to the internal combustion car to maintain ease of manufacturing. So they handle the entire electric drivetrain. So that includes the electric motor and the Drexler limited slip differential all the way out to the half shafts. As far as the tractive system goes, this was handled by 8 electrical engineers and 1 computer engineer. They do all the low voltage and high voltage electric design. So they do everything circuit related. And then there's the accumulator and thermal management system. So because this was a second iteration, and we wanted to really make this design future proof, we had spent a lot of time working on our accumulator to design to make it modular, meaning that all of the all of the side sections of the accumulator could be machined in-house and assembled and bolted together and house all of the high voltage electronics in the car. Thermal management is cooling for the controller and the motor because they do shed a lot of heat. So we did have a thermal management system analyze all of the cooling aspects related to the controller, the electric motor, and the batteries as well. Then of course suspension, almost identical to the internal combustion car. Suspension doesn't care, you know, what powers your vehicle as long as you're able to integrate it. It works the same. So there were a lot of shared components from suspension, and that was very convenient for, you know, the first official electric car design. Next slide, please, Jake. Okay, so here's our CAD model for our electric car. Again, like the IC team, we got pretty far, but unfortunately, we're all stuck at home now, playing on the computer. But this is our first ground up design for our electric car. It features a 420 volt bus battery pack. It can put out 100 amps continuous current. It features an MRAX 228 80 kilowatt electric motor, BAMO car D3 controller. It's a single motor with a chain drive to a limited slip differential, so it's rear wheel drive. And of course, it has a live data acquisition system, which we're very proud of. So we can't wait to test it out, hopefully in the summer. This car is projected to weigh around 400 pounds, which, looking at other cars' data from previous years, is probably going to be one of the lighter electric vehicles in the competition. And that's what we at CSUN are proud of, is the fact that we build some of the lighter race cars, in the competition period. So, obviously, like, you can read the rules and find out for yourself, but you can put as many motors as you want for the electric car. There are some teams that run full four motor cars with torque vectoring and full aero packages, but they also have to have very large battery packs to power and push all the additional weight and aerodynamic loads. But again, we went for like a very light, simple design for our first car. So we're still hoping to get this thing built by the summer. Next slide, please, Jake. Jake, if you want, you can go ahead and take this one.
Oh, sure. So really, talking about the design of a race car, it's all done in CAD, the theoretical model. It is based on a lot of research that you do in the beginning. Really, the whole summer is a lot of testing and research, and that's where we started. You really need to understand what you've been given in terms of like last year's car or cars. They're invaluable resources to figuring out, okay, like what's wrong with it, what can we make better, and so yeah, this is kind of where you start. You're given the CAD models from last year, and you can kind of start working towards what you think, what changes you need to see, and that kind of thing. You go through your PDR where you kind of select your overall design envelope for the car, whether or not it'll be, how light it should be, how much power you should make, what size of an engine roundabout you should use. Those kinds of decisions are made very early on in the design cycle, and then later on you start to really get into the meat and potatoes of it, where you select, okay, well, what differential is the best differential to solve this problem, and that's where you come up with, like, we came up this year, we wanted to use the Drexler. It balanced all the things we wanted. It was pretty low in cost. It performed amazingly. The weight was pretty low. It was simple for us to use because we could just buy it off the shelf and install it. You have your plenum up there, which we do CFD analysis that you have to learn how to do all your internal flow. I'll say that our aero guys on our team were exceptional with CFD. They really spent a lot of time learning the ins and outs. They met with a lot of I know they met up with graduate students to really learn how to do it, and they reached out and they gathered a lot of resources. Bruno was excellent in getting that done. The engine team, a big thing was, making sure we had testing equipment that was good for doing this. So our flow bench had been broken. engine dyno not working, so we got those things fixed so we could actually go through and really figure out what design we needed to do and what would actually enhance the car, and then go back and be able to validate those designs. So yeah, this goes into analysis where then you make your design and then you analyze your design. And this is kind of it's very back and forth. I'm sure Fern can talk your ear off about how many design iterations he went through of the chassis and all the FEA he did. And yeah, it's a lot. And all the different, listed here is all the different things we use: SolidWorks, ANSYS, MATLAB, Ricardo Wave. Ricardo Wave is our internal flow, or 1D flow sim for our engine. We use Excel simulators. We use and we build models. You really get into a lot of really cool design work, and you can get involved in a lot of different things with Formula SAE. We really have a lot to offer. And you have to maximize your design for all your different events, whether it be acceleration, braking, turning, cornering, and then your combination of loads. Last year had a really hard time with that when they redesigned the suspension. It was under combined loading scenarios during your highest loads that we saw failures in suspension, and so yeah, that was so a lot of lessons learned. For manufacturing, we have a very big project, so it's manufacturing is very hands-on. A lot of people get their hands dirty. We not only use our CNC machines that I'm sure you've seen in the Haas lab, but we use the machine shop. That's another invaluable resource. A lot of people are recommended to take the 431 machining class. I've been running the Raise 3D printer. We have our 3D printing that we do where we print brackets and all kinds of things with the carbon fiber, nylon, PLA for rapid prototyping, all that kind of stuff. And then we have our wire EDM, which is a super accurate machine, very interesting piece of equipment. Not many examples of those you see, but that's something unique that we have that allows us to do some like really accurate spline patterns that we can do. Really cool stuff. And then we do a lot of welding in-house. Our whole chassis, both chassis were welded in-house. On our chassis table, you can see an example of someone welding a chassis right there at the top right. And you can see the VF4SS right on the bottom left. Yeah, it's manufacturing. You really get to get your hands dirty, and there's, like I said, like with everything, because Formula is such a big project, you can really get involved with a lot of different things, and you get out as much as you put in. You really do. And then testing. This is the part that a lot of people. It's really fun. Like Morgan gets to take the car out and rip it, and it's pretty cool. And it's very entertaining to go out and watch a student creation go out there and just rip it on the track. And thank you for the heart. And then I'll hopefully this video works, but let's see if it works. But yeah, during testing, you really want to get about 20 hours on the car is really what you want to try to achieve, and that will really shake down the car and show the weak points. Last year failed to do that. It's really hard because we're building such a complex machine now, where in a lot of years past, it was a lot simpler, so you could expedite that manufacturing process. But now it's just become very complex, so testing time has become shorter and shorter, which is really heartbreaking and unfortunate, because after the fact, after the competition, we were able to actually take this car and really put it through its paces, last year's car, and it really just showed itself to be a really great performing vehicle. And we made some small changes and really wanted to hopefully make ours really great too. And unfortunately, it looks like we're not going to be able to do that. But yeah, here's a little video of Morgan ripping it around in the F10 lot.
Does it not allow you to share audio from your computer, Jake?
What did you say?
Does it not allow you to share audio from your computer?
Let's see.
Probably hit same system. Yeah, whatever. Anyway,
yeah, it should be sharing audio. Yeah, I mean, it sounds like I don't know if you've heard a 450 dirt bike engine. You've pretty much heard our car. It sounds like a Kyle bike. But yeah, I don't know if you could see Morgan shift using the sequential shifters there, but that's a pneumatic shifter that it interrupts the ignition, and it actually just slams the transmission to gears. Really cool system. Yeah, right there, perfect. And yeah, so that's fun. You can see a little more of it, but anyway, I'll go on to the next little bit. Yeah, there's another picture of Morgan ripping it at, I'm pretty sure that's Adams. Am I right, Morgan?
That was at SoCal Shootout. So that
SoCal
was
Shootout.
Yeah, that was one of the longest runs we had put on that car. I think that day we put about 50 kilometers of racing on it.
Yeah, and one really cool part about that I'd like to share is that, like, God, what's going on with this thing?
Have you ever used a computer before?
I know, right? It's this fucking mouse. But yeah,
hey, watch your language, buddy.
So one really cool thing about this event was we were one of the cars, we were actually probably one of the most reliable cars out there. Every time they walked up and they're like, hey, other cars are broken down. Are you guys able to go? We were like, hell yeah. So we were really happy, and it's cool because volunteers can come out and you guys can get involved and you guys can go to these events. Even if like next year you're not going to be on senior design, you can come out and do this stuff with us. It's open to everybody. And so it's a very cool learning experience. And yeah, here's the back end. There's that gourd I was kind of talking about. There you can see the rear suspension, the old differential.
Rear suspension broken.
Yeah, rear suspension broken.
So yeah, this is actually the result of a cone hit, and this is why testing is important, because basically we're designing everything to such a low factor of safety that even minor increases in loading scenarios that, like, we were unexpected loading scenarios can break components on this vehicle. So like obviously some things were some components were redesigned after this, but I mean this is just from hitting a cone. So you can see how fragile this car has become, because it's become so light and weight optimized. So that was kind of where we realized at the end of last year, hey, we should probably step back, and that's when Dr. Prince actually made the decision to make reliability the number one goal. But again, that's just the importance of testing and your design validation. So yeah, it's definitely not a perfect process, but yeah, it's all encompassing, and I wouldn't have done anything else. And I guess before anyone has any questions, from Dr. Prince himself, he's expecting only one senior design class for next year. So like this year there were two separate ones, but for next year it will be between 20 and 25 students that can join the official senior design for the A section. Basically, you guys will be either using or taking both cars from this year, whether or not we complete them, and you'll be racing them for next year. I know that he will want you guys to still do, research, design, and manufacturing on your own. What that will be, I don't know. Maybe there has been talk of going to a carbon fiber monocoque chassis, and if that's the case, that's a monumental leap forward, because you guys can basically cut 25 pounds off of a car that basically weighs 330 pounds. I mean, that's substantial, and is a huge amount of design points in the process. Additionally, the electric car is still under development, and will probably take a couple more years before it's functioning at the same level that the internal combustion vehicle will be at. So whether or not you guys end up building two of your own cars or one of your own car, it's kind of up to you guys and how driven you are and what you guys want to do. Dr. Prince is a bit of a hard ass, but he's also a reasonable man if you have a plan. So if you come to him with a well thought out formulated plan that, you know, details exactly how many points you will earn in each event if you go to this new design, he will oblige your design proposal. So he's definitely open to, you know, innovation and, you know, doing things that everyone else thinks is kind of crazy. So, you know, don't think that you're just stuck in a rut and you're going, okay, we have to just, you know, basically make the same car from last year. Like that's not the case. There were a lot of design changes from last year that, you know, that we proposed to him that initially he was a little hesitant on, but again, like once we, you know, proved to him with our theoretical designs and we backed it up with our calculations, you know, that's when he acquiesced and decided to, you know, let us go forward with the process. I feel like I've been rambling on here for 20 million years. So if there are any questions, feel free to ask now.
I have a question.
Yes.
What classes do you recommend to help with formula?
So I think, Jake, we put that in.
We put that in
our workshop cues, but I can list them off now. So we would recommend, I mean, obviously, I think the prerequisites for senior design are 309 numerical methods and 330 machine design, and I think, don't quote me on this, but I think 386 finite element analysis is a co-requisite.
Yeah.
And then as far as recommended courses, ME 460 is vehicle dynamics. If you want to do suspension, ME 462 is internal combustion engines. Obviously, if you're into internal combustion engines, you want to do that. ME 431 is machine design and manufacturing. So if you want to learn how to run CNC machines and manufacture components in terms of machining, you should take that class. ME 384 system dynamics. ME 435 is mechatronics. ME 436 is mechanics and design of composite materials. So if you wanted to get into aerodynamics or composites, those are definitely some good classes to take.
I'd like to add one thing. Keep in mind that with those classes, you don't necessarily have to take them before you get into senior design. If you're interested in a particular sub-team, I would recommend trying to get into them for the fall semester of your senior design, taking it with it. You will get a lot of the information a little too late, but it will put you into contact with a lot of the professors you need that can help answer your questions and help guide you through the design process. And you're going to need help. Like it's not something you could just, you don't just come in knowing everything. And so yeah, it's just, that's one thing I'd recommend.
And then as far as volunteering, obviously, I mean, we're kind of in a weird situation where we all have to kind of sit at home right now. So obviously volunteering is kind of put on a standstill. But you know, this entire team, both, you know, internal combustion and electric, you know, want to see this program, you know, succeed for years to come. So, I mean, obviously, not only will we be around either in the area or, you know, online to answer any questions that the new team has, but, you know, we're going to be around over the summer to hopefully get the car built and at least get both cars built and get some testing in and kind of bring you guys in as we go along throughout the summer. So if you guys want to volunteer, as soon as we're kind of allowed to be outside again and the quarantine's lifted, we'll be finishing our cars and testing them. So if you're trying to get on for senior design next year, you need to volunteer. And we'll definitely keep you guys posted as far as, you know, when you want or when we would be either working on the cars or testing them. And we'll have that information on the FAQs that all the teams are going to be submitting.
How is the selection process going to be if there's only 25?
That's a great question. It's it's kind of a combination of, how much, how much work you're putting in on a weekly basis. And I mean, basically, for the most part, like the people that volunteer, they're we end up getting to know them by, like, name and face. And if it comes down to the fact that we need to kind of sort through and make a selection between one volunteer versus another, maybe we'll do some kind of interview process just to kind of see something a little bit more in depth. But yeah, I mean, we've never really had an issue like that in the past, but if it comes down to it, I mean, we'll have to kind of analyze that in a case by case basis. But yeah, we're usually just looking for people that are dedicated, that want to learn. Again, like, you don't need any experience. Most of us have never turned a wrench before, but as long as you're willing to learn, I mean, that's more valuable in our eyes versus someone that knows a lot but might be kind of a dickhead to work with.
Cool. I have one last question. I don't even know why I'm asking questions, but I have one more.
Okay.
So, like, how does one get selected as a team lead or the project manager?
I don't think you do. I think people just kind of pick you. For instance, I didn't want to be the project manager for the electric car. I just wanted to do suspension, but everyone else had kind of decided that for me, which is okay, because usually that ends up working out the best, but not always. It's usually Dr. Prince will have the final say for the project manager. But as far as the team leads, those are typically elected by the team members themselves, because that usually just, but most people will kind of recognize who they want to listen to ultimately. And especially if you have a group of people coming from, like, let's say ASME, who have all worked before together, they may just fall back into the same groups on each respective sub team.
So we got a question in the chat, or oh yeah, so Sean talked about that. Our team needs more hands-off compared to, yeah, that absolutely not.
No.
I mean, I gotta say it kind of depends, but usually no. I mean, there's a lot of work to be done at the team level, and so usually not hands-off at all. And honestly, it depends on what you mean by hands-off. In the lab, team leads are very hands-on, usually even more so than others. And that's usually how team leads get selected, is usually they're the most dedicated, the most the most knowledgeable maybe on a subject, or they have some extra experience that makes them good for leading that sub team. But definitely not more hands off. I wouldn't say that.
Yeah, so
it's definitely the opposite.
There he is.
There's
Josh.
Waiting for him.
Josh is building cars.
So the project manager is basically responsible for making sure that everything gets done on time and all the logistics. And then, like, the team leads are responsible for basically, essentially knowing the most about that sub system and communicating information back and forth between the project manager and the individual team members, because 40, 50 people are, that's a lot to manage for one person. So it's a lot easier to deal with 5 or 6 people, and then have that information distributed amongst all the team members. So the team leads typically will compile a lot of information, and they'll be responsible for, like, let's say, submitting documents throughout various points in the year for the competition.
So
sorry, I meant PMs. Again, like, do you mean design wise? Like, what are you trying to get, like, hands off? Because I mean,
it depends. Like I know that
it really depends.
A lot of the times, like, if Morgan and I are usually very busy with working on other parts of the project, so usually we don't get our hands dirty per se. in the lab so much, but that doesn't mean that there isn't times where I have, or Morgan's probably a little bit more hands-on than or definitely is a lot more hands-on than I am. But I mean, I picked up angle grinders. I've done stuff in the lab, a couple times. So there's opportunities, but in terms of like it being your job, it's really not. You're really more of like a paper pusher, I'd say. But it just kind of depends on. I mean, it just depends on what part of it depends on how it also depends on the team. Like sometimes the team doesn't lend itself to that.
I think the best way to describe the project manager is you're in charge of the big picture, right?
Yeah.
Like you lead the team to their overall goal. Like you work with the rest of the team, but ultimately it's the project manager and Dr. Prince that decides on the goals of the car of whatever particular year you're working on it.
Yeah. And it also depends on what Dr. Prince, how he visualizes the team that year. Sometimes Dr. Prince sees the project manager differently, and I think it just depends on the team. So just if you go into any of these specific things, just make sure you keep an open mind about things and not be afraid to take on new challenges. Just really just try not to be afraid of things. Just that's what I would recommend. Send it. Yes. So the finance team does count as a team. It is a sub team, and that's definitely the what keeps the team going. And if you're interested in that, we have our CFOs who do a lot of management and stuff of that side of the team. And that's also a management style position. Like our last CFO, he just got a really good job at Northrop, I think, doing composites. He got a really nice starting salary, and so that's another cool job to look into. Definitely, there's a lot of jobs on Formula SAE that are unlike any other job that you can get on other senior designs.
Any more questions, guys? Or is that good? I think that might be it.
All right, I guess it's time to wrap up the meeting in that case.
I'll stop sharing.
They're probably done listening to us.
Dude, I'm done listening to you.
All right, thank you, Armando.
All right, guys. Thank you guys all for coming out. Thank you to the senior design students that presented their senior design projects. I appreciate it. We had 50 members in the Zoom call at one point, which is crazy. I did not expect that many people to come out, so it's just awesome. We'll be posting this recording on our website, and we'll put timestamps for every senior design in case you got here late or you want to, re-listen to one of them. And we'll be posting out an update on Slack, and we'll send out an email soon. Do you guys have any more questions in terms of ASME events? All right, well, in that case, we'll end this meeting, and I'll see you guys in 2 weeks for Evening with Engineers.
Thank you, Armando. See you later.
Thank you, Armando.
Thank you guys.